Hello, everyone, and welcome to Beyond Bandwidth, Leviton's podcast series where we dive into network technology's hottest topics. I am your host from Leviton Network Solutions, Roy Chamberlain. This conversation shines the light on AI data centers. In part 3 of our 4-part special edition to this series, Leviton's Mike Connaughton hosts the panel discussion as Nick Taylor of Network Center in the UK takes his turn by speaking on cooling technologies and challenges in the data center space.
Following Jonathan will be Nick Taylor, who is the Technical Director at Network Center in the UK. Nick provides pre-sales and technical assistance to ensure the right products and services are selected by talking to customers and understanding project requirements. With over 25 years in the industry, and RCDD NTS certification and regular standards committee attendance, he ensures that customers get the best advice. Pertinent to us today for today's discussion, Nick spent a number of years working for a professional services group working on cooling optimization using CFD to fix cooling issues in existing data centers. Nick's going to be talking about developments in the cooling technologies as it heads towards AI networks.
Thank you very much, and thank you for inviting me here today to talk to you about this. I'd start by saying that the information I'm going to put across is based on what we have in the UK. I imagine it probably applies to some other countries as well. All over Europe, you hear that there are problems with power. Don't know if some of you have heard of FLAPDA. So Frankfurt, London, Amsterdam, Paris, Dublin. There's also Madrid. These are sort of the financial centers of Europe. And pretty much everywhere is saying that they don't have enough power. Although I'm going to talk to you today about cooling, I thought that I would just sort of point out some of the biggest issues that we face in the UK. So the first one is power. So it's the generation of power, but it's also the infrastructure. So how we get the power from where there might be a future, power station to the locations that are required. The national grid, as it's called in the UK, is quite old. It's creaking already. Got huge demands, air source heat pumps, electric vehicles, data centers. I mean, you name it. The growth in the requirement for power is exponential. We've also got the Paris Agreement the UK is looking to adhere to. So we can't just start burning fossil fuels. We don't have that option. And renewables, of course, only work some of the time. So we're looking for something to take the base load. There's talks about small modular reactors from the likes of Rolls-Royce. Legislation's very, very difficult in the UK. And it's like to be sort of at least 10 years, probably 20 years before we get to see any of those. So putting aside those huge issues, which really relate more to the building of new data centers to support, AI, I wanted to focus on what some of the challenges are supporting AI and high performance computing in existing data centers. So some of the issues in no particular order. So the weight, for example, right? So it goes without saying, you've got a rack full of equipment that's air cooled, and then you want to take the equivalent number of servers and put them using immersed liquid cooling, right? Significantly more weight compared to racks. So some existing facilities, whether it's an on-prem or an off-prem colo data center, they've got to pick very carefully the locations within their facility that might be able to support it. Connectivity, which Jonathan's already covered, sheer volume of cables, point-to-point or structured cabling. There are some other issues which perhaps we might discuss later on about things such as the sheath types, right, that need to be used when we're talking about immersing servers, fiber connectivity, and obviously the issues that you get with if you're not using AOCs. But today I'm going to focus on the cooling of the capacity and infrastructure. Just to cover the different sort of cooling types. So the basic principles, just to cover them, I'm sure most of the people who are listening today will know this, but the majority of data centers around the world use air cooling because it's easy and because it's considered to be safer than liquid cooling, but it's not the most efficient and it can't support the highest heat loads. And another basic principle, so temperature and airflow are both factors, but I often hear the misconception that people think that things can be fixed by just lowering the temperature. Of those two, temperature and airflow is the biggest factor there. There's no moving away from that. Compared to air, water has significantly higher heat capacity and faster heat transfer properties as well. So much better suited to higher heat loads of AI. Lots of people don't like the idea of distributing liquid around their data centers, but it's worth remembering that actually we're just turning full cycle. 50 years ago, things were water cooled. IBM mainframes were water cooled in data centers. The facilities were designed for it. You would have drip trays and drains underneath raised floors in data centers and things. This is not new stuff. I mean, it's new in terms of the levels of heat that we're looking to take away, but this is not difficult. It's not new. It's not anything that we can't get around. But I guess the main issue is that within the existing data centers we have today, they're not designed for that. What kind of upgrades and things need to be done? So in terms of air cooling, air containment, so it's a physical barrier that separates the supply and return air from the IT equipment. It can be done on an aisle, 2 rows, a single row, or even on a rack. I'll show you some more on that later on. Rear door heat exchangers. So basically, hot air comes out the back of the rack and is cooled before it enters into the room. So you could build a room without any additional airflow at all. I literally just use rear door heat exchangers. Direct to chip liquid cooling. So where we're taking liquid up to the chips. So basically air can't cool them quick enough. It needs to be cooled using liquid. But also worth remembering, even with direct to chip, you still need air cooling as well, because there are other things within the servers that obviously generate heat and they still need to be cooled with air. And then immersion liquid cooling. So just a little bit of background. Before air containment, I'm sure many people in this room probably remember it. I was talking with a colleague earlier about an air traffic control site where there were about 100 racks in there, and they were all facing the same direction. And obviously, as you got further down the room, the heat got greater and greater. But the kind of general model was that you'd have rows of racks. They'd be set into aisles of 2 rows, backs of racks facing backs, fronts to fronts. You'd have a raised floor. You'd have perforated tiles in the floor. The cold air would be sent from the perimeter air handling units under the floor to the front of the racks, hot air out the back, and return to the units. For those that can't see the images, the top image is a principle of how it's meant to work, and the bottom image is the reality of it, which is basically the hot and the cold air mixes. When the hot and cold air mixes, the delta T, the difference between the supply and the return temperature, is reduced, and that basically leads to very poor efficiency. So very quickly, as we needed to start supporting higher heat loads, we moved away from that. So the logical progression from there was cold aisle containment. So essentially taking that same room, putting doors and a roof, sometimes just doors, and basically making sure that you separate the hot and cold air. The problem with it is that the basis of what didn't work before still doesn't work now. A raised floor was meant to provide an equal pressure across the whole of the room, but it never worked like that, especially if you had things underfloor like pathways, things like that. There was a lot of work within sort of TIA and other standards to tell people where to put pathways to try and minimize that kind of stuff, low down in the cold aisle, high up in the hot aisle, and so on. Having done a few measurements in my time with the bolometers, with some of the CFD studies we used to do, I can tell you that there are some all sorts of strange effects that you can't really account for. You suddenly come to a tile and the pressure will be really low. So if you've got to put IT equipment in that particular rack, if there isn't sufficient airflow, it's going to pull it from somewhere else. Cold aisle worked reasonably well, but a lot of companies would suggest that before you put a roof and a lid on it and seal it up, you probably want to do some airflow studies first to make sure that it's going to work as you'd expect. Hot aisle. So hot aisle containment is what the vast majority of new data centers are in the UK anyway, and I guess probably around the world. There's usually not a raised access floor, although there could be. It's normally a slab floor. The cabinets go directly on the slab floor. All of the pathways for power and data are overhead. The cold air can come into the room in a number of ways, but generally in the larger data centers, it's an entire wall at one end of the room where the air is just pumped into the room. So it goes through the racks, up through like a unichimney, so a single chimney that works for 2 rows of racks, usually up into the ceiling plenum and then back to the units outside. Certain locations around the world, it's free air cooling, so the air literally pumped in from the outside of the building, some humidity control with that. This is what we see in the vast majority of data centers. There are some different versions of hot aisle containment, often called chimney racks or vertical exhaust duct racks, where if people want to deploy a rack at a time, they can do that. But again, we don't really see that much in the UK anymore. It tends to just be hot aisle containment. Rear door heat exchangers. Yeah, so As I say, the principle of this is that, say, for example, you've got a data center that's designed for, say, 5 to 10 kilowatts a rack, and you've got some racks where you need support for 30, 40, 50 kilowatts. There's a number of ways that you can deal with that. One way, if you've got a data center operator who's prepared to extend the heat rejection plant out onto the floor, is to use rear door heat exchangers. And there's quite a few different versions. There's passive ones that don't use fans, so they rely on the servers to push the hot air through the heat exchanger. Or if you want higher heat loads, they often have fans on them that basically just pull the air through. Some people don't like the idea of the fans in case they fail, but obviously designs and things can work around those. And there are some setups where people are getting over 150 kilowatts per rack by using a rear door heat exchanger. So it's an interesting way to extend heat loads. So direct to chip usually has a CDU in the bottom of the rack, so a cool distribution unit. If you like, rather than extending the coolant out to a rear door heat exchanger, instead you're taking it to the CDU. The CDU has individual connections that go directly to the chips. They basically deal with that side of the cooling. As I say, air for the higher heat loads is not enough. And then the air cools the rest of the servers. And then obviously with immersion liquid cooling, instead of blowing cold air, you submerge the entire system into a dielectric liquid. I'm still quite amazed by this when I see it, seeing servers dropped into in this liquid. It doesn't conduct electricity, obviously, otherwise it wouldn't work. But it does cause all sorts of other issues. Like, for example, if you want to use normal patch cords, the sheath will not survive. Most of the sheaths that we're using these days are kind of PVC or low smoke zero halogen along those sort of lines. Neither of those are good enough. Fiber connections, obviously fiber connections rely on minimizing loss between two connectors. You put normal fiber connections into a liquid like this, it doesn't work properly, hence the reason of using AOCs. So yeah, those are pretty much the methods of cooling, obviously the later ones that we're going to need to support AI in our existing data centers. What can we do to make sure the data centers we've got can support this? So talking to most of the co-location centers that are looking to do this, they're kind of saying, look, we're limited on the amount of AI stuff that we can support. We can't get a lot more power to the facility that we've got. So essentially what they'll be looking to do is get a room that might have had 50 racks in before and basically put a handful of racks in the center of it. And if it's immersed liquid cooling, obviously you're talking about a significant weight in a particular location within the facility. Perhaps you can spread that out, but then you've got issues with cabling, so you kind of need to have it in place. So there are limitations perhaps physically to where you can put these. There's a lot of wasted space. Is that the best use income provider for the facility? So most are looking to sort of look at something like a small area of the data center to support some limited kind of kilowatt per rack AI clusters. So things like NVIDIA GB200, those are the sorts of things where they're unlikely to be able to be supported. Any existing DCs can support AI is basically the answer. It's just that they can't be supported, most of them, for the sort of medium and higher heat loads using air. And the fact is that in the UK, 99% plus use air cooling. So they're going to have to be quite a few changes in order to support it.
Beyond Bandwidth is a podcast series produced by Leviton Network Solutions. For more information on the topics we talked about today, as well as other enterprise or data center network infrastructure content, or to check out all available episodes of Beyond Bandwidth, visit us on the web at leviton.com/beyondbandwidth or wherever you normally listen to podcasts. If you enjoyed this episode, we'd appreciate you leaving an honest review in your podcast application. Along with word of mouth, leaving a review will help others find our show. I'm Roy Chamberlain, and this was Beyond Bandwidth. Until next time.